All right, now we're going to be working on actually just solving a bunch of equations. All right, on this page, we're solving exponential equations. And sometimes, most of the time, they'll want both an exact answer and a decimal approximation. All right, so we're going to go ahead and get started. All right, so when you start with an exponential, when you start with a variable as an exponent, what you want to do first is you want to think, can I get the same base? On both sides. Okay, that's what you want to think of first. Second thing you would want to do is isolate the exponential part. Okay, you know, if you can get the same base on both sides, then you do this page, what's on this page. Okay, but if you can't, then you're going to isolate the exponential part. Okay, so that's kind of like, can I get the same bases? If so, do what's on this page. Or you're going to come in and isolate the exponential part, then log or ln both sides. So it's almost like, the first thing is almost like when you tried factoring, when you had a quadratic, because it was easy. Then if it didn't factor, you went to the quadratic formula. That's kind of your approach with exponential equations. So before I get started on this one, I'm looking at the 5 and the 15, and I realize right off the bat, I can't write 15 as 5 to some power easily. The exponential part's already isolated. So I'm going to come in and log both sides. All right, now our normal approach is to just use either log or ln, which is log base 10 or log base e, because those are the buttons that are on everybody's calculator. That's typically how they'll show it. Okay, then that x, in the exponent, we can use property 3 of logarithms to bring that down. Okay, and I really want you to do this as you're doing it. Do it in the right order of steps, not just how it should look at the end, but like what led you there. It just starts making more sense when you do that. So now you have x times log of 5. And remember, log of 5 is just some number. So if we need x by itself, we now have an easy equation because this is linear right here. This is now linear. It's amazing. So we're going to divide by the log of 5, both sides. Boom. We're going to have x equals the log of 15 divided by the log of 5. All right, now compare that to problem number 2. So on that one, I'm going to look. I notice a 2 and an 8, and I think, I can get the same base. So I'm going to take a moment to rewrite the 8 as 2 to the 3rd, and that's being raised to the x minus 6 power. So because I could do it, I'm going to change this problem so that I have the same base on both sides, because you'll see how nice that is. Okay, so then I can multiply the exponents, because that's how a power raised to a power works. And I'll go ahead and distribute that. That would be 3x minus 18. Now I'm not canceling the 2's. That's really wrong thinking. I'm not dividing by 2. I'm undoing it. And I know I can undo that basically by logging base 2 on both sides. We don't normally show that. We just say if we have 2 to some power equals 2 to some power, we know these have to be equal. And that's the normal process on these problems where we can take advantage of that one-to-one property. Okay, really, I'm doing this. It's just nobody likes to write it. But that's why that worked. I just log base 2. Since it's the same base on both sides, I just log base 2 both of these. Okay, and then that undoes that and gets you x plus 4. Log base 2 undoes the exponential, and I get 3x minus 18. But it's normally, we just don't normally write that. We just do this. Okay, so now you might subtract the 3x. Okay, that'll be negative 2x plus 4 equals negative 18. okay, which means that negative 2x was negative 22, which means x is a positive 11. And, you know, if you were careful with all your arithmetic, there's no chance that that's not going to be an exact answer, okay, that's going to be the answer. So you can check it, but you're not checking it because of potential domain issues. You're just checking to make sure you didn't mess up something, okay? All right, and then over here, our answer didn't turn out so nice, right? So what you typically do on that is you go in and you do the log of 15, close the parenthesis, divided by the log of 5. Okay, and that's going to turn out to be 1.683, about 1.683. So that's the decimal approximation. And the exact value is the log of 15 divided by the log of 5. Okay. Now look at number 3. On problem number 3, okay, on that one, if that had just been a 64, we would have been home free and we could have done what we did on question number 2. See, if that had been a 64 and if we had this equals 64, then we could have had this be 8 to the second power, and this was already an 8. And so then the exponents we could have set equal to one another, okay? But this one's not a 64, it's a 63. So what we're going to do is make sure the exponential part is isolated, which it is. Now we can come in and log both sides. Okay. All right, then this exponent, using property 3, can come down in front. I want to see that step. I want you skipping to the final finale here, okay? And then what's left after you bring that down is the log of 8 equals the log of 63, okay? Now at this point, algebraically, you might think, well, I'm going to divide by the log of 8, and that'd be okay, but this particular problem gets pretty messy because of that 4x plus 1. So I like to go ahead and distribute this. So I would get 4x log of 8 plus 1 log of 8 equals the log of 63. Okay. And then you've got to kind of, when you're looking at that, it can be overwhelming. Since you're new to logarithms, you look at that and just think, oh my gosh. But in reality, log of 8 is just some number, and so is log of 63. So this isn't as bad as it looks, okay? It's just x times a number plus a number equals a number. I mean, it's like a 2x plus 5 equals 13 is what I want you to feel, okay? So what I want you to think about is that this is what you're trying to get by itself. You've got a lot of stuff to undo. So I'm going to start by subtracting the log of 8 from both sides, okay? All right, when you do that, you'll have the 4x log of 8 on the left side. On the right side, you'll have the log of 63 minus the log of 8. And the logs don't go away, and you don't say 63 minus 8 either, okay? All right, now you're really close, believe it or not, to the exact answer. This is what you're trying to get by itself. You have 4 and the log of 8 multiplied it by it. So if you could divide by those things, then the 4 would go, the log of 8 would go, and sure enough, you would just have x on that side. And then all of this right here, believe it or not, that's your exact answer, okay? Now, this is the thing that during our online class session, I really asked for people to try to type that in because it's really hard to do correctly. This is a grouping symbol. So you need an extra set of parentheses around the top and the bottom for it to perform that the way it's written. And it's really not good practice to do this and write it down, do this and write it down, do that and write it down, because you wind up compounding your error. And you're liable to get an answer that's further away than it should be from the exact answer. So we're going to do the log of 63. Okay. Put that in parentheses. So make sure you have parenthesis, log of 63, close the parenthesis, minus log 8, close the parenthesis, but then close another parenthesis for the whole entire numerator. Then divide by, open a parenthesis, put a 4 in there, then put a log of 8 and close it twice. Okay, when you do, this turns out being about 0.248. Okay. All right, and that kind of makes sense because if you put that in right there, put that 0.248, I usually do this just to kind of check, especially on a test. 4 times 0.248 plus 1 is almost 2. It's 1.992. And I know 8 to the second would have been 64. So that looks good. Okay. You don't have to check it, but we're going to. I told folks we could probably omit this one. I worked it out on the worksheet that I posted in document sharing. So if you want to look at it, you can. The algebra on this one is a real bear because of the fact the bases are different and that you have 2 terms here and here. So it's a super messy one. I just felt like that was something we maybe didn't need to focus on. Okay. All right. And then we did this problem in class, in the online class. We were going to do this problem. And so we noticed the variable is in the exponent. So before we do any log stuff, we've got to get that by itself. We do that using techniques we've known for a while. Subtracting 1 from both sides, and then dividing by 3 on both sides gets the exponential part on a side by itself. And then because this is an E, I actually have a button on my calculator that is a pure inverse to that. Okay, you know that log would need to be base E to undo to be an inverse. Okay. And log base E of E really does give me x minus 2. Okay. Oh, I meant to tell you something else before I did that. Log base E is really ln. So that's really ln of E to the x minus 2. And that log base E is really ln. Okay. And if you do natural log of something that's base E, see how the bases match? So that is what you're going to have left. It's really composition of functions. It's really, you're doing one function after another, but they're inverses, so they completely undo each other. All right, so for an exact answer, x would wind up being natural log of 33 plus 2. And then if you need a decimal approximation, make sure you're using the ln button on this one. You would do ln of 33, close the parenthesis before you add 2, and you get about 5.497. Okay. All right, now you might forget to use natural log when you have base E. This whole problem still would work fine if you used log. It's just it would have a few more steps at the end when it came time to simplify. All right, I'm going to get you started on this one, but this is another one we don't need to focus on so much. This problem is really quadratic in form. Okay, you know, that exponent is really twice that, so it's kind of like if you had something like this. If you had like x squared minus 6x plus 5, okay? That's really just a quadratic equation, and you would be doing that problem by probably factoring, right? Using an x and an x, okay?